International standard atmosphere. Vinny, shout it out to me. What is it?
1,013 millibars.
Yep.
At 15 degrees C.
Perfect.
122. I can't remember the.
This is 1225. You're correct, but you don't need to know that. I've never come across a question on that in the exam. But yes, bang on. And what about the temperature and the pressure changing with height?
So the temperature is every 1,000 feet decreases by 2 degrees, 2 Celsius. Sorry.
Absolutely, yeah. And pressure?
Pressure.
No, you're very
gone.
Full house. What happens to pressure?
It decreases.
1 millibar every.
Is that 1,000 feet as well? No, 500 feet. 500.
So bloody close. What is it, Nick? 1 millibar per.
Is it 1 millibar per 30 feet? Or is that something
30.
else?
Yeah, 30 foot.
No.
Yeah, that's right, isn't it?
Yeah.
Okay, guys, you've got to commit this all to. You just got to know all of these things. Yeah. You won't pass any exam. Doesn't matter what exam it is without ISA being in the top of your head, because it appears in every bloody exam. Right. So grab your whiz wheels first. Now, you might well find there's questions that will ask you about temperature. Now, if you've got a really silly, simple question in the exam, then you've definitely got an RTFQ, because they will nearly always throw in a wobbler into the question. And a common wobbler is that they'll put in degrees Fahrenheit. So have a look on the bottom of your computer. Can you see there's a scale that's marked? And on that scale, you can see that it's got centigrade and Fahrenheit. Yeah. Can you see that on the bottom of your CLP computer? And that's how you can convert centigrade to Fahrenheit quickly. So if you get anything to do with ISA and it starts talking about the rate of change of temperature and it's Fahrenheit, that's how you can quickly work it out. Right, so as Vinny quite rightly pointed out, pressure changes with altitude. It changes by 1 millibar every 30 feet. So we've got 3 different sorts of ways of measuring how high we are above the Earth's surface. So I'll draw this classic diagram that you see in every textbook. With an airfield on the top of a cliff next to the sea. Now, the altimeter has a little subscale on it, doesn't it? You can twiddle it round, and as you twiddle it round, the needle moves, so you can set the base point at what the altimeter is reading relative to. So the first thing we come across is QNH. So QNH means your height, or how high you are relative to the sea. In other words, this is NH means nautical height. Which is where the expression comes from. So QNH is altitude above sea level. So when we're flying around in the circuit, we want to be 1,000 foot above the ground. Because we want all the planes to be 1,000 foot above the ground, don't we? So what we do when we're flying around in the circuit is that we set QFE on the altimeter. So QFE stands for field elevation. In other words, the altimeter is reading how high we are above the ground. Now, of course, as we all know, particularly those of you that's done MET, is the air pressure not only changes every single day, but it changes throughout the day, and it changes all over the country. So the pressure, so the sea level pressure at Larnaca might well be different from Paphos and might well be different from Akrotiri. In other words, if you put an altimeter in a dinghy and you went to Akrotiri, Larnaca and Paphos and you adjusted it to read 0, which, let's face it, that's what QNH is, you might well find that the pressure difference at those 3 places might be different by one or two millibars. So QFE is very much a local thing that's just relative to a Pacific airfield, and it's obviously based on the pressure setting at that unique period of time, and it's primarily based on, of course, how high the airfield is above sea, which of course is fixed. All these things are based on something called the mean sea level. So as far as we're concerned, the sea doesn't go up and down. In other words, we have a mean sea level, which somebody's determined that's the level of the sea. Now, thinking about this a bit more, what is the purpose of QNH? What sort of things do we want to achieve when we're talking about setting our altitude above sea level. I mean, why is that even important? I mean, what do you reckon, Ross? I mean, why do we actually bother? I mean, you know, we could set QFE height above where we take off from, and we could set QFE to the airfield we're going to eventually land at. I mean, why do we actually want to bother with QNH? I mean, who cares? I mean, what's its significance?
Well, if you practically wanted to have a reading of elevation above the ground, you'd have to change it all the time.
Yes, well, why is it important to actually know how high we are above the ground?
Well, terrain changes a lot.
Yeah, absolutely. Because do you remember we talked about this before? This is Membry mast. What are those two numbers here, Ross? This 1191 and the 504 in brackets.
Well, 504 is the base at above mean sea level, and the top number is the top of the mast above sea level.
Yeah, that's not bad. 1191 is the height of the top, is the height of the top of the mast above mean sea level, correct. 504 is how high the mast is actually above the ground at that
Yes.
We had a 50-50 chance. It was a good shot. So yeah, so really then, when we're looking at terrain clearance, as Ross quite rightly pointed out, we've got to know how high we are above sea level, because that's what everything on the chart is relative to. So we would have to make sure, if we wanted to, say, be safe and fly 1,000 foot above everything within 5 nautical miles of our track, we would really be wanting to fly around near Membry services on the M4 at about 2,200 feet above mean sea level, wouldn't we? And that would give us 1,000 foot above above the Membry mast, so that if the weather starts getting a bit rough, visibility starts to get a bit dodgy, starts to rain, you're starting to get distracted because some air traffic controller is asking you for estimates to places you can't even find on the ruddy map, and diverting you to places that you don't even know exist, then you really need to know how high you are above everything, so you don't accidentally crash into something. So, yep, Ross is dead right in that the first thing we're using QNH for is obviously terrain clearance. What else do you think, Nick, that we are using QNH for?
Just because it standardizes how high you are above the surface.
Absolutely. Why is that important, though? You are correct. I'll give you a little clue.
For after the transition layer, obviously when you're a bit, no,
That's
so you don't crash into stuff.
Sorry?
So you don't crash into things. Is that what you're going for there?
Not things, but it's supposing that you've got all of these aeroplanes and air traffic control is giving you a height to fly at, you want to make sure that you're at your 500 foot from crossing planes all the time. So in other
Yeah.
words, it's very important that all the planes flying in one area are all using the same QNH value. Because otherwise, if air traffic control says to one plane, fly at 2,500 and tells another plane to fly at 3,100, and those planes have got different QNH values set on their altimeter, well, that isn't going to work, is it? So generally, all the planes in an area are all flying the same QNH. Now, how on earth does that work? Because we've already said that, well, hang about. QNH changes all over the place, and QNH constantly changes throughout the day. You know, maybe it changes, you know, every 20 minutes it might change, particularly when there's a front coming over. We've already said in Met that pressure drops very quickly. So it could change very rapidly. It could be changing a millibar every 15 minutes, may not be uncommon. And of course, in the vicinity of a front, there might be 2 or 3 millibar difference over 50 miles. So how on earth are we going to make sure that all the planes are flying the same setting? Well, the way we do that is that in the world, everywhere is divided into altimeter setting regions. So in other words, you might have the whole of Cyprus might be one altimeter setting region, for example. And what happens is just before each hour, all the various air traffic controls within that altimeter setting region and Met offices will kind of compare all of their pressure settings they've got, and they would decide on what's the lowest value and what's the forecast value, in other words, what's happening, and they would choose a regional QNH setting for the whole of that area. So every plane in that area for that hour, for the next hour, will be having the same QNH set on their altimeter. And it's the lowest forecast value for the whole of that area. In other words, if you've got that QNH set, you're going to miss the masts. So that's what we call regional the regional QNH. So the QNH is useful at low levels. When I say low levels, I mean typically levels below about 8,000 feet would be considered a low level. In other words, in Europe, that's going to be below most of the mountains you're going to find. But when you start dealing with passenger jets and you start to get very high and you start to deal at sort of like sort of 20, 30,000 feet, well, QNH is kind of irrelevant really, and the planes are flying so fast that you don't really want to keep up changing the QNH, and the QNH doesn't matter. Who gives a toss what the QNH is if you're at 30,000 feet? So what happens is that when you're flying very high, like right up here, whoops, sorry, that plane looks like a donkey. That really has got a few problems. If I can draw a bit. When you're very high, these planes all use what's called a standard pressure set. And what they do is they actually put 1013 on their altimeter subscale. And anything relative to 1013 we call a flight level. So flight level 210, for example, you add 2 zeros on the end of a flight level, and that gives you the height in feet. So flight level 210 is 21,000 feet on the altimeter when you've got 1013 set as your subscale. That's what a flight level is. So that means we've got three things that we're using. We've got Q and H, which is what we're going to be using most of the time in a light aircraft. We've got QFE, which is what we're going to be using for landing and taking off. And then we've got flight levels, in other words, standard pressure setting, which is what we're going to be using for longer distances, or any time where you're getting involved with airways and long distance work and things. You know, you'll always be given the flight level to fly at. So how does this affect us if we're flying from high to low pressure and low to the other way around? I mean, Ross has already talked about the fact that we've got to have the right Q and H value to give us the right type of terrain clearances. Well, let's talk about, there's a nice slide on it. So this is just a recap of Q and H and QFE, which we've talked about, and of course flight levels where it's relative to 1013. Now, of course, although it's drawn here, the 1013 higher than sea level, well, bearing in mind that may not be the case. 1013 might be lower than the sea level. I mean, depending on whether the Q and H is greater or less than 1013 for that particular day and that particular time, and that particular area, of course. So don't necessarily. So now we've already said that the pressure can change quite substantially when we're dealing in a frontal system. So what happens if we kind of don't change the altimeter? In other words, we take off, we get the Q and H, and we just keep flying, and we don't bother to update it. Well, this diagram says it all. It's saying when flying from high pressure to low pressure, the altimeter overreads. In other words, you're actually lower than you think you are. So the rhyme to remember is, if flying from high to low, beware below. So remember that little rhyme for the exams. Flying from high to low, beware below. In other words, if you're flying from a high pressure to a low pressure and you don't reset your QNH, and you've worked it out that you should be you've got plenty of room, at least 20 foot over the top of memory mast, and you can't see memory mast, then you're probably going to crash into the top of memory mast. If you're flying the other way round, if you're flying from low pressure to high pressure, that's not quite so bad, because you're actually going to be higher than you really think you are. So you'll think you're going to be at sort of 2,000 feet above sea level, and you're actually going to be, say, 2,100 feet above sea level. So that's the rhyme to remember. Flying from high to low, beware below. Yeah. So this is what we're just talking about. So in other words, if we're flying from one airport to another airport, they're obviously going to be at different heights above sea level. So we'd use the QFE to take off with, we'd use QNH en route, and then we'd use the QFE to land. And if as we change from one air traffic control to another air traffic control, as you leave in the circuit, they quite often would give you the updated QNH value. Where else could you get the QNH from? If you're doing a long journey, you know, where would be places you could find the QNH? What do you reckon? What do you reckon, Robbie? Hi, Robbie. Ideas where you can get the QNH from? You've been flying for an hour and a half, so you know that your QNH is going to be wrong. Have a think. Well, how on earth could you get the up-to-date QNH?
You can just radio out and call out for it.
What?
Just radio out and call out for it.
Hey, anyone know what the QNH is out there? Doesn't sound very professional, does it?
No.
What sort of other things could you do? Well, there's lots of things you could do. For example, you know, we're like at Akrotiri, we've got we've got an ATIS that's transmitting all this information. Well, nearly all airports have this. So you could just find somewhere that's any sort of large airport en route, and you could actually tune into their ATIS, couldn't you? And just listen to it. Even if you've got no intention of going there, if you were flying from Paphos to Larnaca, you could probably tune into the Akrotiri ATIS on one of your radios and just listen to what the updated QNH is, which is always a good crack. There are other frequencies dedicated to volmets where you can listen to all this information as well. And of course, the other great thing is that if you talk to any air traffic control en route, they will give you the updated Q&H as well. So, and of course, you can write that on your plog. And of course, on your plog, you've got a gap at the bottom. You've got gaps at the bottom here. And as you get the new Q&H, you'd write Q&H 1015 or something like that, wouldn't you? So that you'd keep all this up to date. And then, of course, you could update your altimeter. So what's the when you're doing your cross countries, what's the A for, Nick? You know, Frida, what's the A?
Sorry, can you say that again?
You do your cross countries and you do your Frida checks.
Yeah.
What's the A? Have a good guess.
Altitude.
What we're talking about.
Hey, good deal. Yeah, altitude.
Altimeter set.
Altimeter. Yeah. So for checking your Q&H and
In other words, you've just got the Q&H and you've just got it. That's what the A is on Frida. Yep. So that's the last thing you do. Yeah. Okay. So let's quickly talk about regional Q&Hs. So on a UK chart, and Cyprus is very similar. You've got altimeter setting regions, and I'm just going to find one here on the south coast. There's one that goes through Bognor Regis, just to the right of it. Here we go. Here we go. This is it here. So you'll notice that, do you see this strange line that looks like a set of dumbbells? This is showing you the altimeter setting regions. And you'll see that to the east of that line, we call that the Chatham altimeter setting region. And to the west of that line, it's the Portland altimeter setting region. And as you could probably imagine, that you see this like dumbbelly kind of line. This dumbbelly kind of line does in fact sort of extend throughout the whole chart and sort of divides up, and the whole chart is divided. If you look for them carefully, you can follow these altimeter setting regions, and you can find out which altimeter setting region you're actually in. And if you were flying near somewhere like Farnborough, where it's right close to the two regions, they would actually give you two Q&Hs, and they would say something like the Chatham Q&H is 1017, Portland Q&H 1018. Of course, you know, you've got to know which one you're in and which one you're intending to fly in. You know, you're going to look a bit of a penis if you get back to Farnborough and say, which one am I in? Golf Charlie India Yankee, you do actually have a license, don't you? just want to make sure. I've got my the lights. That's better. Now, So we've talked about how you convert from QNH to QFE. So you're flying towards this airport, and obviously, when you start talking to this air traffic control, they'll give you the QFE. Now, of course, you can actually work out what the QFE is probably going to be, can't you? Because if you know how high the airport is, then obviously how high the airport is above sea level is what their QFE is going to be based on the QNH. So it's quite easy to work or to take a guess what their QFE is going to be. So if we were going to fly a bit higher and a bit further, though, we'd want to change from QNH to standard pressure, because we would probably be given a clearance from Paphos when we are approaching Paphos on our way to, say, Santorini. We would be given a clearance to sort of overfly Paphos, probably at 3,500 feet on the Paphos QNH of 1019 or something, which would be a typical clearance for Paphos, routing via Tobol, which is a reporting point just off the coast of Paphos. But as we were approaching this reporting point, they would ask us to climb to a probably flight level 850. Sorry, flight level 85. I've got to make sure I've got this right. I don't give you crap there. I've got to do the maths. Yeah, they'll ask you to fly to flight level 85. Climb to flight level 85. So in other words, you would have to then set 1013 on your altimeter, and of course that's going to change your height you're actually at, your apparent height you're at, because it's now relative to 1013, and you'd apply power and climb to flight level 85. But you might be able to see there could be an issue here, because we've already said that one of the reasons for QNH and flight levels and things is to make sure that we're all flying at the same pressure setting, so that all of the aircrafts have the same pressure setting, so that when you hear on the radio that you're flying at flight level 85 and there's somebody else flying at flight level 90, you know that you're going to be 500 foot away from them. But there's like a sort of there's like a sort of grey area, isn't there, in the middle? Because there must be a point where, as you change from sort of like planes at say 8,500 feet on the QNH and planes at flight level 85, I mean, how far apart are they going to be in the air? In other words, if you hear on the radio a plane's at 8,000 feet on the QNH and you're flying at flight level 85, are you safe, Nick? Are you going to be 500 feet away from that plane? They're flying at 8,000 feet on the QNH, and you're at flight level 85. How far away are you from that plane, assuming that you crossed?
Depends on the QNH then. So what did you say the QNH was?
Well then, bang on.
I thought you were trying to ask me to do some quick maths then. I was trying to think of what it would be, but
No,
yeah, never mind.
well done. You're dead right, Nick. Excellent bit of observation. And I deliberately didn't say it. And Nick is absolutely correct, because how far apart those planes are is just purely a function of how different the QNH is to 1013. Now, if of course the QNH just happened to miraculously be 1013, those two planes would be 500 foot apart. But it might not be. So that means that we have this kind of area between flight levels and QNHs, a sort of like no man's bit, and we call this the transition layer. So that's the transition layer is the difference between the flight level and the QNH, but for the same value. So I've got a nice, I've got slide number 37 shows me that, which I think is the next one after this one. So here we go. This is where it talks about the transition layer. So you can actually see the transition layer might be 0, or it might be huge, depending on the difference between the Q and how different the QNH is from 1013. Exactly as Nick pointed out. I did once. I was flying to Sardinia once, and I was flying there from Menorca, and all the seasoned pilots at Menorca were saying to me, "Oh," he said, "You sure you can get back okay? The pressure's looking a bit low today." I'm going, "Well, I've got an instrument rating. I've got an instrument quick plane. Do I give a toss? So the weather's going to be a bit crap. I don't mind." And everyone I bumped into, and I told them I was on the way to Sardinia, said, "Oh, I don't know about this, Paul. It looks a bit low pressure to me. Are you sure you're going to be all right?" I'm thinking, what is this fascination about the low pressure? Anyway, so I jump in my plane, fly all the way to Sardinia, and was sorted out this problem with the plane that we had to go and fix. I jump in my plane, ask for clearance for taxi, and air traffic control says, "Sorry, but you can't fly back to Menorca today because the pressure's too low." And I said, "What? What do you mean the pressure's too low?" And they said, "Oh no, what happens is that because the pressure's so low, there isn't enough space now. The transition layer is so big that there's an airway going to Sardinia, but there isn't one on the way back because it's so low. The 500 foot's been cancelled out." I was like, "Well, what do I do now?" "Well, not a lot. You book into a hotel." Oh, piss. And yeah, you learn. So Now there is a sort of trick exam question about errors in the altimeter and how that affects things. How that affects separation. Well, all altimeters are calibrated within 50 foot, but altimeters don't, they don't always compensate for the temperature correctly, and they don't compensate for the pressure altitude correctly and the air density correctly. Does it make a difference? Well, it's a trick question in the exam. If you think about it, no, it doesn't make a difference. It doesn't affect separation. And the reason it doesn't is because if you've got density errors and temperature errors, all the altimeters that's made all have the same error. So that although they read the same QNH, as you fly different heights and the pressure isn't a linear change because of the temperature change is not a linear change, then it doesn't matter, because two planes at 8,000 feet are still going to both be reading 8,000 feet. They're just not 8,000 foot exactly above the ground. So that's the answer to that question. In other words, they've got their plus or minus 50 foot, but the altimeter error is common to all altimeters. You know, in other words, the temperature density errors that they've mentioned in the exam. Right, so I need to talk a bit about the why I chose flight level 85 to fly to Sardinia. But I am getting worried at this point. Why I chose flight level 85 means to fly from Paphos to Santorini. So I might be buying a lot of beer if I've got that wrong. So we all know there's two sorts of flight, IFR and VFR, and depending if you're going east or west, depending on that, that depends on how high you fly. So we've got two things. We can either fly IFR or we can fly VFR. Each of these has what's called the semicircular rule, and this is 0 to 179 degrees. This is 180 degrees to 359 degrees. And if we're flying VFR, what we do is we fly odd. We have odd here, and we have even here. We have the same thing if we're flying IFR. We have even over here. We have odd here. And it goes, a VFR goes, it goes 15, flight level 15, in other words. Then it goes up in threes. That'll go. That'll go up. What it goes up in twos. That's going to be goes up in twos. That's going to be 5-5. That'll be 7-5. And then the evens are going to be 1,000 foot on top of all of those. So that will be 2-5. Then it'll go up in 2, 2. So with 1,000 foot above that, 4-5. That will be 6-5. 8-5. And then if we're flying IFR, then that's the intermediary values. That goes 10, 30, 50, etc. And then this goes 1,000 foot above that. That goes 20, 40, 60, etc. Oh, so I don't owe you all a beer. That was a stroke of luck, wasn't it? So that means if we're flying from Paphos to Santorini, VFR, we would be flying at flight level 85. Here we go. Of course, after flight level 85, there would be it would go obviously 105, and it would just increase, you know, in 2,000 feet. So what flight level it would go like this. In other words, 10,500, 12,500 feet. But this is really, when you're flying long journeys, you don't really want to be flying above 10,000 feet. I mean, you can do, if you're fit and healthy, you don't smoke, you might be able to fly at you know, the whole journey at 10,500 feet. So this is how you would pick your flight level for the purposes of flight planning. So you'd have let's just put it on here. Let's just increase this one here. So flight level 7.5, flight level 9.5, and then we had another 2 would be 1.1.5. So assuming that you don't want to fly above 10,000 feet, Vinny, if you were flying from Santorini back to Paphos, what flight level would you choose to come back at?
Flight level 9.5.
Yeah, flight level 9.5. This would be your return, yeah. I was flying back from Santorini once to Paphos, and I'd filed in my flight plan, flight level 9.5, and the air traffic control said, "Oh, Golf Hotel Romeo, climb flight level 210." And I said, "Yeah, 21,000 feet." I said, "Negative. Be advised, we're single engine piston equipped aircraft." And air traffic control said, "You single engine, you wish to declare an emergency?" And I said, "No, be advised, aircraft is designed and built with one engine." "Oh, you fly with one engine?" You know, they had no concept of a plane with only one engine. Right, so let's put all that lot to bed. It would be pretty mean of somebody in the exam to expect you to have that table memorized. You can actually, just remember though, if you do want to memorize it, it's not as difficult as it seems, because it actually goes up in 2000s on each bit, and you've just got to remember that that VFR goes 2515 and IFR goes 2030. Or, no, it goes 2010, but and it goes 30, of course, 2010, 2515. And then, of course, you can then construct the entire table. So, right, now we need to talk about climbing and descending. So there's quite often a couple of questions on, or a question on climbing and descending. So we've got to think about how long it's going to take us to climb, but more important, how long it's going to take us to descend. So we've already said that if we're flying from Santorini Paphos, we've already said that in that direction we're probably going to be looking for flight level 95. In other words, potentially 9,500 feet. Yeah. Now, Paphos will expect us to descend to overfly Paphos probably at 3,500 feet. Will be a typical clearance that Paphos will want us to be at. They don't want us to be in the whiskey. There's an airway whiskey 195. They don't want us to be in the airway. We'll want to be descending here. So now, what's a typical descent rate in a light aircraft? Well, a descent rate can be anything you like, really. But if you want to value your ears and you don't want to get tinnitus in a later life, you'll be looking at a descent rate of 500 feet a minute, or if you can, you'd probably be looking at more sensibly a descent rate of 400 feet a minute would be about what you're looking at. So you're looking at a descent rate of 400 feet a minute. So how long is it going to take you to descend from 9,500 feet to 3,500 feet? So Robbie, what do you reckon? How long is it going to take you to get from 9,500 feet to 3,500 feet at 400 feet a minute? If you could do that calculation for us.
Four minutes. Let's see.
Have you done that? Have you done that on the calculator, or is that
No, I haven't yet.
a useful shot in the dark?
15 minutes.
15 minutes. So how did you do it? You said that 9,500 to 3,500. You subtract off those two, and that's 6,000 feet. Yeah. So you've got to descend. You've got to descend 6,000 feet. Yeah. At 400 feet a minute. So if you divide 6,000 by 400, that gave you how many minutes? 15.
15.
15 minutes. 15 minutes is quite a long time, isn't it? And if your ground speed is say 120 knots, how far away then, Vinny, do you need to start descending? If your ground speed is 120 knots. The distance equals speed times time. So the distance is going to be equal to 120 times 15 over 60.
Got 1,800 divided by 60. 30. Is that going to be miles?
30 nautical miles. So really then, I mean, this is quite, I mean, you think about this, I mean, that means we've got to start our descent, Tobol, which is just the other side of Paphos, 30 miles out at sea, 30 miles away. That's an awful long distance, isn't it? 30 miles, we've got to actually start the descent. And it's going to take us 15 minutes. Now that's assuming we've got a 400 feet a minute rate of descent. Now, if you can, I would always recommend a lower rate of descent even, and I always choose myself, I always descend at 300 feet a minute on a long journey. Air traffic control might cop the arse and tell you that they don't want you to descend at 300 feet a minute, they want 500 feet a minute, but if you can, I mean, this is a nice rate of descent that's not going to damage your eardrums. Descending at 300 feet a minute. 500 feet a minute is for long, you know, that's when your ears keep going pop and you have to keep clearing your ears all the time because you're, you know, that's about, 500 feet a minute. But most planes, most commercial passenger jets nowadays are looking more like 350 feet, which of course is a much more friendly rate of descent. The other reason why I generally descend slowly over a long period of time is that if you do get a problem, if you get an engine failure, for example, if you're descending at 300 feet a minute, you might well be much better in radio contact, and you're going to be higher, aren't you? Whereas you're going to be closer and higher. So it can be beneficial to have low rates of descent and high rates of descent. Thinking about some other issues, right? So that's how we do timed descents, and of course that you would do timed climbs, absolutely no different. In other words, if your plane climbed at if you worked on a climb rate of say 800 feet a minute, as a cruise climb, you're obviously not in China, India. But if you're working out 800 feet a minute cruise climb, well, you could do the mathematics. You could work out how long it's going to take you, and you could work out your, you know, what your ground speed is. You could work out how far your distance covered is going to be. You could, that means you could put on the plog your climb, because you're going to have reduced airspeed, so you could work out, yeah, blah blah blah. You can guess that you would have how your plog would look like if you were doing a long protracted out climb, because you'd obviously have to take that into account in all your mathematics. So let's, so we've really cut, we've talked a bit now how we're going to fill in all of these boxes in a typical plog. And you've got some columns in your plog. Let's just so the idea is you would finish up somewhere along in all plogs. You'd finish up with your heading, which would be magnetic, and how long it's going to take you in minutes. So this would be a typical plog. For each leg. So you'd have heading, let's say, is 0.95, and the time is going to be say 22 minutes. And then you've got another column which would be ETA, and so the idea is what you would do is that when you're on this leg, as you start this leg, you would just take 22 minutes onto the time now, which is 2:05. So you'd write 4:07. So what you would do is, as you're flying along, you would then know that when you get to 4:45, you'd then be able to look for the waypoint ahead of you, the waypoint that you're actually looking for, this particular point. When you actually get there, you write in your updated or your actual, and you'd write in there, say 4:06. As you write in, as soon as you've written in 4:06 there, you turn on to a heading of 150. You add 31 onto 4:06, and 31 onto a 4:06. I've picked a right cracker one there. So we get what's that? That's 7 7. So that's 1. So I write 16 here. That's my new ETA on a heading of 150 degrees. And that's how you would keep your plog updated through flight. You'd be constantly rewriting in your new ETA at every waypoint, ready for the next waypoint.
Well, so you calculate the ETA based on that formula: distance, speed, time.
No, you can't do that in flight. Oh, you've got to be joking. The human brain hasn't got any capacity for that, Ross. So you've already calculated these times on the ground before you even took off. Your whole plug is filled in apart from your ETAs. Yep. So your ETA is just filled in on flight. So as you get to each waypoint, you just add your time that you previously calculated onto your actual ETA on your actual time of arrival, and then you would write in the new ETA for your next waypoint.
So I don't understand. Where do you get 47 and 46 from?
I looked at when I shouted out the time, I looked at my computer clock on the screen, and I added 22 onto it to get 47.
Oh.
Because it's I said, oh, the time now is 2:05, looking at my screen, and so I just said 2:05 add 22 is 47. That's my new ETA. And then I said, so what we do is, as we're getting close to there, to 47, we would then start looking around for our waypoint. And when we actually got to our waypoint, we'd update our actual time of arrival, which could be anything, which could easily be, say, 47. We turn onto our new heading of 150, and then I'd add 31 onto 47, which would be 78, which would be 18. So that means our ETA for the next waypoint is going to be 18 minutes past.
So revised ETA is when you arrive at the waypoint.
Yes. In other words, you arrive at the yeah. In other words, this is a bit crappy, really, isn't it? That shouldn't be called ETA. This should be called actual. I think we'll change those plugs and we'll call it the. We won't call it revised ETA. We'll call it actual, because I think for a PPL plug it should be actual. It should just say actual, shouldn't it? Instead of ETA, this should say ATA. That's a good point, though, Ross. Yeah. And that's really how we're going to keep the plug updated as we fly. And the plug, this is what's called dead reckoning. The plug would actually work quite well, but it does rely on a few things. It does require you to fly accurately. By accurately, I mean fly that heading. Yeah, so it's got 095 here. If you're flying 075, 085, 105, 100, 080, the probability of you finding your waypoint is not high. You've got to be flying these things sort of like plus or minus 5 or 10 degrees to actually have a ghost in hell's chance of flying accurately enough to actually reach your waypoint. If your legs are small, like for example, we get to this point here and our next heading is say 175 degrees and the time is 4, you might need to use fractions of a minute. So you might need to use, you might need to use 4 minutes, 30 seconds. You might well find that rounding up or down, is just isn't going to be accurate. Generally, legs that's less than 10, you quite often will need to bring in the seconds if they're within, if they're halfway between. And your plog needs to be neat and organized. And of course, you need to keep your DI and your compass aligned. On your Frida checks, your D of Frida. So last thing I need to move on now with talking about time. How do we measure time? Now, right. Everything in aviation is based on Zulu time. Zulu time is basically Greenwich Mean Time. So in the good old days, when Britain ruled the waves and all that sort of stuff, is that the time at Greenwich, the clock at Greenwich, at the Greenwich Observatory, which was calibrated to the stars and things, that was what we call Greenwich Mean Time. In other words, that was the time the whole world based it on. However, things have moved on, and we now we don't use GMT anymore. We use something called UTC, French Universal Time Coordinator, and UTC is basically GMT, but it's just a slightly more accurate way of representing Greenwich Mean Time. You can always tell when you're looking at it because it will have a Z at the end. So the Z at the end means Zulu. If you have a time that's 12 o'clock and it has an L on the end, that's local time. Now, of course, if you're flying a long journey in, say, a passenger jet or a ship or anything like that, then really local time is kind of meaningless concept. That everything is based on Zulu time, and all your flight plans and everything, and when you get winds and when you look at TAFs and METARs and they give you periods of validity and things like this, everything is based on Zulu time. Sometimes you'll get, particularly in taps and meters, you'll see things like, for example, you might see 2, 4, 1, 7. We'll just see a group of 4 digits written like that, and that actually means the 24th of the month, and this bit means 1700 hours Zulu, in other words, time now. So this is how you quite often see dates and times. Sometimes you will see period. You might see something like 241739. And once again, this is the month, and the 1739 is hours and minutes Zulu. So how do we know the difference between, we talked about time, how do we know the difference between day and night? Well, obviously, one's black, one's isn't black, but that's obviously not a bit more technical. Now, each country has a different way, or well, not it, every country is different, but you'll find that there are regional differences throughout the world as to what they consider to be sunrise and sunset, and what they determine to be night and day. Generally speaking, twilight is when the sun is 6 degrees below the horizon, and dawn is when it's 60 degrees below the horizon. In other words, you know, because dawn is before you can see the sun, isn't it? I mean, you can't see any part of the sun when it's dawn, can you? It just suddenly starts to get light. And when it starts to get light, in this in the latitude we're in at the moment, that's when it's 6 degrees below the horizon. And we call this civil twilight and civil dawn will be this magic 6 degrees. So in other words, this period of time, the twilight time, is bigger than actual sunrise and sunset. Sunrise is defined as soon as you can see one speck of the sun, that's sunrise, and as soon as you can't see one speck of the sun, that's sunset. So obviously day and night is extended by the twilight zones. So how, for example, how do you know the, for example, the when it's day and night? Because Yeah, there is quite a bit in the in air law relating to day and night. Well, you have to find this out in the country that wherever you tend to fly in. Now in Cyprus, I'll see if I can quickly find it. I might not be able to find it. Let's just see if I've got it here. So the DCA, for example, publish, yes, here we go. Right, I should be able to find this. Right, the DCA publish the VFR guide. Here we go, this is what it looks like. And if we just quickly scroll through this, it gives us all of the VFR minimas, the heights, the laws relating to things, night VFR, day VFR. This is why we have to know the difference between day and night, because there's all sorts of, you see that everything here is based on, is different day and night. And of course, to fly at night, you need a night rating. Here we go. You see lots and lots of things here, day, night, differences. So I'll quickly scroll through all of this, and here we go. And you'll notice that what we get is what's called this table that they publish, and you can go through this, and it says here the times in the table are given in UTC for the beginning of civil morning twilight to the end of civil evening twilight. And that's basically the difference between night and day. And you'll see that they actually give you the exact hours that what is defined as night and day. And you normally find that you've got a chart like this for most countries. You can actually find out what the night and day is based on these angles of the sun relative to the horizon. Right, so I'm going to finish today with talking about a bit more about, or we'll start talking about when things aren't quite right. So up till now we've talked about the plog, and we've covered how to fill in every single box in this plog. We've talked about how to fill in the airspeed to work out what your ground speed is, what your true airspeed is. We've talked about how we use the whiz wheel to find out our ground speed based on the wind, and what our heading's going to be to fly the desired track. We can then transcribe all of that into our plog, so we actually know where we're going from and to, track distance, altitude. We get from our computer our heading and our ground speed, and then we can calculate these various other things. That we can calculate how long each leg's going to take us, and then in flight, of course, we can then update our ETAs as we go along in flight. But life's a bitch, and sometimes things don't go to plan. And there's quite a lot of these 1 in 60 rule questions in the exam. So what is the 1 in 60 rule? Well, what the 1 in 60 rule is, it's quite a useful thing that we use in not just flying. I use it in marine navigation as well a fair bit. If I have something 60 nautical miles a leg, say 60 nautical miles long, and I have, and we have something 3 nautical miles here, like for example, we are flying from A to B, and we finish up at C. Whoops. We want to know the error. In other words, we want to know what this angle here is. Theta. Now, we could physically draw this, which is impossible to do in flight, obviously. Or we could use a calculator. If you can remember your trigonometry of working out tan and arctan, you remember opposite over adjacent and all that sort of gear from your O levels, you could do it fairly simply on a calculator. But there's a nice feature in that for small angles of theta, the tangent is roughly 1 in 60. So we know that theta is going to be 3 degrees. So in other words, if I take a 60 nautical mile leg and I measure 3 nautical miles here, that's going to be, whatever that is in nautical miles, that's going to be what that is in degrees. Which is, you can imagine, is quite a useful thing to have, isn't it? What a very useful thing to know. So if this was not 3 nautical miles, if this was, say, 5 nautical miles, then theta would be 5 degrees. Let's leave 5 nautical miles there. If this was 30 nautical miles, Nick, what would theta be? If that was 30 and that was 5, what would
2.5?
we
Or
have?
would it be 10?
Where's that, 50-50?
So isn't it either half of 5 or double 5? I can't remember which way it goes.
Well, it's a bloody good safe bet, isn't it? Let's face it.
Yeah.
All right. Well, let's think. Let's just think about it, Shay. What we're saying is, if we've gone 30, and then we go another 30 to get to make this 60. What we're saying is after 30, this is going to be 5, all right? So if that's 5 after 30, what's it going to be after 60? Looking at this diagram.
10.
Yeah. So in other words, if we shorten the distance, the error is going to be more, isn't it? And the same's true is that if let's just change this to be 120. So what do you reckon then, Vinny? What's theta if that's 120?
It'll be half,
Half of,
5, so 2.5.
that's going to be 2.5 degrees. In other words, it's going to be, whatever that is, whatever this is, relative to 60, isn't it? So if I just make this x, then we could actually imagine that theta (60/x), yeah, degrees. So if x is 120, it's going to be 60/120, obviously times the error, yeah. So you can probably start to see how this is going to come into. We're going to have quite a few formulas based on this. So there's loads and loads of questions on this in the exam. So what we're going to do is that tomorrow I'm going to do quite a lot of mathematics based on these 1 in 60. So I think we'll call it a night there. And then tomorrow we're going to start talking about track corrections. In other words, when the plug doesn't work and we're flying from A to B and we fly along for that 20 minutes, and after 20 minutes or whatever, we look down at the ground and we go, my waypoint's coming up. Oh shit, my waypoint is over there.